welcome back to another explainer. Today, we are jumping right into the nuts and bolts to unlock the top-down architectural blueprint of modern SystemVerilog test benches. If you've ever felt completely overwhelmed by the sheer number of moving parts in the Universal Verification Methodology, or UVM, you are in exactly the right place. We're going to completely demystify the UVM component hierarchy, taking what looks like a wildly complex web of code and turning it into a clear, logical, and incredibly powerful structural framework. By the end of this, you are going to have a crystal clear mental model of exactly how, and more importantly why, a UVM test bench is put together. So let's get started.
Here is our quick roadmap for today. We're going to cover the overall UVM test bench architecture, then look at the top-level test and environment components. From there, we'll dive inside the UVM agent, break down the top-down build phase, and wrap things up with some essential best practices and connections.
All right, part 1, UVM Testbench Architecture, Modular and Reusable. Let's get right into why we actually need a layered architecture for our verification environments in the first place. To really wrap your head around UVM, you have to think about it spatially. It's helpful to visualize this hierarchy like a corporate organizational chart, or honestly, kind of like a set of nested Russian dolls. Out at the very outermost layer, we have the test itself. Inside that test sits the environment. Inside the environment, we place our agents. And finally, nestled securely inside those agents are the dedicated components that do all the actual heavy lifting: the sequencer, the driver, and the monitor. Data and configuration flow down through these specific structural layers, while transactions flow between them. Now, this structure is entirely deliberate. It's what allows us to decouple our components, making them incredibly modular and super reusable across entirely different projects. Moving on to part 2, we're looking at the top level, the test and the EV, or environment. Let's start at the very top of our blueprint. The UVM test is basically your master control node, but the absolute key phrase to remember here is dynamically created at runtime. Because the test is dynamically instantiated, it means you can compile your heavy, massive test bench just one time, but you can run dozens or even hundreds of different tests against it just by passing a command line argument to your simulator. It's an incredibly efficient way to manage a large verification suite. So the test operates as the chief orchestrator, right? And it holds 3 massive responsibilities. First, it literally brings the top-level environment into existence. Second, it configures that environment. Maybe it's tweaking parameters using the factory or the configuration database to suit a specific test scenario. And third, it applies the actual stimulus by invoking sequences. It is the brain of the operation, directing the entire flow from the very top. Stepping one layer down, we find the UVM env, or environment. If the test is the brain, think of the environment as the body. It's our main structural container. It holds all our interrelated components, our agents, our scoreboards, our coverage collectors, all together in one logical place. By encapsulating everything targeting your design under test within this single environment block, it means you can just pick up this entire environment and drop it inside an even larger system-level test bench later on. It's brilliant for reuse. All right, part 3, inside the UVM agent, grouping components. Dropping one layer deeper into our environment, we hit this fundamental building block of the UVM topology. An agent is essentially a specialized wrapper class. Its entire purpose is to group together the sequencer, driver, and monitor. But why group them? Well, because an agent is dedicated to one specific protocol interface. Say your design has a PCI interface and an Ethernet interface. You're going to have a dedicated PCI agent and a completely separate, dedicated Ethernet agent. This keeps your structure highly modular. If you need to verify a brand new chip tomorrow that also uses Ethernet, you just copy and paste your entire Ethernet agent over. Boom, done. What's fascinating here is how the agent's internal workings elegantly split into 2 distinct camps: the active participants that physically talk to the design under test and the passive observers. When an agent is configured as active, it uses its sequencer and driver to push data into the hardware. But when it's configured as passive, the sequencer and driver are actually disabled and only the monitor remains active to silently watch the bus. Let's look at the active side first. The UVM sequencer acts kind of like a valve or a traffic cop. It manages the execution and arbitration of high-level transaction items, stuff like read packet or write data. It hands these abstract items one by one to the UVM driver. Now, the driver is literally where the rubber meets the road. It translates those abstract transactions into the actual binary ones and zeros wiggling the hardware pins on the clock edges.
On the flip side, we have the passive observer. The UVM monitor sits completely independently from the driver. It just watches the interface pins. Whenever it sees a valid protocol transaction occur, and it doesn't matter if it was driven by our test bench or by the hardware itself, it packages those pin-level signals right back up into a clean, abstract transaction object. Then it broadcasts it out to the rest of the test bench, like the scoreboard, using what we call an analysis port.
Part 4, the top-down build phase, constructing the test bench. We have our blueprint beautifully mapped out, but how do we actually construct this in code?
This is a great question. In standard SystemVerilog, keeping dozens of complex class objects synchronized during creation is an absolute nightmare. You could easily have a driver trying to drive data before the monitor is even constructed. So how does UVM solve this massive synchronization challenge? It solves it using phases. The crucial point here is that UVM perfectly mimics physical construction. Think about building a house. You have to lay the foundation before you can build the first floor, right? In UVM, the build_phase executes strictly top-down. The test builds the environment builds the agents build their drivers and monitors. This entire process happens strictly in order, establishing the perfect hierarchy, all before a single nanosecond of simulation time actually advances. And to do all this building, we lean heavily on the UVM factory. Rather than just using standard SystemVerilog new constructors, we ask the factory to create our components. Why go through the extra step? Because the factory allows us to swap out components at runtime without changing a single line of our original code. If you want to replace a standard driver with an error-injecting driver, you just tell the factory to make the swap. The environment code doesn't change at all. It's a real game changer. So what does that actually look like in practice? Well, inside the build_phase, instead of just writing out a typical constructor, you use the factory create method. You pass it a string name for debugging, but pay very close attention to the second argument you pass, the keyword this. By passing this into the creation method, you are handing over a pointer to the current parent component. That single little keyword is the magical glue that formally registers the new component, like a monitor, as a child of the agent, permanently locking them together in the UVM topology. Finally, Part 5, Best Practices and Connections, Guidelines for Reusability. Let's talk about industry standards for wiring this whole system together and allowing the data to actually flow.
Okay, so we've built the hierarchy top-down, but now we have to wire all those blocks up. We do this in the connect phase. Interestingly, the connect phase executes bottom-up. Once all the components physically exist, we can start connecting their communication pipes, which in UVM are called TLM, or transaction-level modeling ports. Connecting these TLM ports is wonderfully clean. You simply call the .connect method. You might connect a producer's port directly to a consumer's export, or a monitor's analysis port over to a scoreboard's implementation port. This architecture ensures that the monitor doesn't need to know a single thing about the scoreboard. It just writes to its own port, and the UVM infrastructure magically handles the delivery. It is total decoupling. Now, another absolutely crucial tool for connecting our test bench to the actual hardware design is the config.db, or configuration database. Think of this as a highly sophisticated, globally accessible post office for your test bench. Instead of manually passing variables down through every single tedious layer of your hierarchy, from the test to the env to the agent to the driver, you can just place a configuration object in the database at the top level, and the specific component that needs it can reach out and grab it directly. Think about how we pass virtual interfaces, the actual pointers to our hardware pins. At the top of your module, you use the set method to drop the virtual interface into the database, labeling it with a string path like VIF. Then, deep down at the leaf node of our hierarchy, the driver, you use the get method to pull it right back out. You've instantly bypassed all the middle management layers of the hierarchy, keeping your code super clean and isolated. To wrap up our architectural blueprint, let's quickly run through the absolutely critical best practices derived from these source guidelines. Always register your classes with the factory using the standard macros. Always use the configuration database to distribute your virtual interfaces rather than hard-coding paths. Always strictly decouple your component communication using TLM ports. And finally, when you actually start moving time and generating stimulus in the run phase, make sure you are raising and dropping objections properly, or your simulation is going to end at time 0. We've seen how this nested hierarchy, paired with the factory and TLM ports, creates a verification environment of unparalleled flexibility. You now understand the blueprint, so I want to leave you with this provocative thought.
If this architecture allows us to completely decouple our stimulus from our structure, what exactly limits how far we can reuse our verification components across entirely different projects and companies? Honestly, the only limit is how strictly you adhere to the blueprint we just laid out. Thanks for joining me on Miss Deep Dive, and I'll see you in the